Hello, I'm Mike McCulloch. Today I'd like to go into the history of inertia a little bit. And the starting point is the initial ideas of the ancient Greeks. So Aristotle, for example, who believed that the default state of motion was for things to stay in one place. He thought that things tended to achieve their own state of equilibrium and then just kind of stay in the same place. And he also thought that when you dropped two balls of different mass from a great height, that the heavier one would fall more quickly, which makes sense in that kind of model, because the larger object has more mass. So when you hold it in your hands, you can feel that it has more mass pulling it down. So it's kind of logical to assume that it would fall more rapidly under greater force. What they didn't know was they didn't know about inertial mass, which means that heavier objects also find it harder to accelerate. So Aristotle's ideas went on for a long time until about the 5th century, just in the latter stages of the Roman Empire. I guess the early Eastern Roman Empire. There was a guy called John Philoponus, and he had a radical idea. He said that instead of things, I should go back and say that the problem with the idea that things stay in one place is that you can't then imagine that the Earth orbits the Sun. Because if the Earth is moving around the Sun and you think that things like to stay in the same place, then everything on the Earth should be falling off it and being left behind. So it was very hard for Aristotle to accept the heliocentric model of the solar system, which had already been proposed by then. But anyway, John Philoponus in Alexandria, about 450 or something like that, he said that Aristotle could well be wrong, and that he proposed the idea of an impetus, which is something that you give a body by pushing on it, that is stored by that body, a bit like our concept of inertia, that keeps it going, a bit like a kinetic energy. So he proposed this, and he also did experiments dropping balls of different sizes like Galileo later did, and showed that they all fell at the same time. Large objects, small objects fell down at the same time, hit the ground at the same time, which fits better with the inertial model, because he at least admitted there was inertia, and so larger bodies also found it harder to move. And this was an anticipation of the later idea that things just keep going in a straight line unless you stop them. But it wasn't complete. So John Philoponus proposed that this impetus only lasted for a certain amount of time before it was kind of dissipated by friction, which is not quite our concept of inertia. The concept of inertia was taken further by the Arabs in about the 12th century by Avicenna or Ibn Sina, and other ones about the same time. And they regarded it as being, I think it was al-Baghdadi as well, who said it's a permanent property and it doesn't dissipate with time, which is closer to our model of inertia. And then Galileo said more or less the same thing, but made it more mathematical. And then Newton came along and made it mathematical as well, and used it to model the solar system, the planets, with his second law. But our concept of inertia still has this concept in it that something has been put into the object, some momentum, if you like, that we give it, and it's stored in the object. This is kind of a holdover from John Philoponus's idea of impetus. But what quantized inertia does is it takes away all that. It argues that inertia is not an inherent property of a body. It's caused by its interaction with its environment. Because if you just take Galilean dynamics and then assume that the speed of light is a limit, which is what Einstein did, then what you get is whenever an object accelerates, it sees a horizon behind it. And then the new idea of quantized inertia is that this horizon damps the quantum vacuum behind the object, pulling it back. So this means that inertia is not, as I said, innate in bodies, but it's due to their interaction with the environment, which gets rid of this, finally, this idea of impetus, which was fantastic at the time, 1500 years ago, but we can now get rid of it. And so the change to inertial mass that this makes is very tiny. It's very tiny, but it means that we can finally model galaxies without the need for dark matter. And it also means that if inertial mass and motion is determined by the environment, then we can make things move by manipulating the environment. So this is the idea behind QI thrusters. And okay, so I hope you've enjoyed this short, and I look forward to seeing you next time. Goodbye.